So here, I'm going to go ahead and introduce you to some of our shortcuts that make finding derivatives easier. And these are designed so that we're trying to find the derivative without having the x plugged in. In other words, we're coming up with an equation that will give us the slope values for a function. And once we know this equation for the slope values, we'll plug in the x we want. These videos are going to go through the rules pretty quickly. You may have to watch the video multiple times. You will definitely need practice on these, but the nice thing is we have tons and tons and tons of practice throughout this entire course on these rules of differentiation. So they will get easier. They will feel, some of them will feel frustrating right now, but they will get easier. So here are kind of the main rules. These aren't the only ones, but these are the main ones. The constant rule, the power rule, the constant multiple rule, sum and difference rule, product rule, quotient rule, and then the chain rule I'm actually going to save for later. I want to make sure that you get rules 1 through 6 and start to feel comfortable with those before I throw the chain rule in there, because that's the one that tends to cause the most confusion. So with the constant rule says, if I have a function that is a constant value, then its derivative is 0 for every x value. And this is easiest to explain graphically. So here I have a function, f of x equals 8. The graph of that is a horizontal line. Well, because the derivative is the slope of the function, the slope of this function at every single point along this function, the slope is 0. So that means no matter what x is, f prime of x will be 0. So then for the power rule, this is probably our most commonly used derivative rule. If I have a function of the form x to the n, the important thing here being that the base is the variable, the exponent is a constant. If that's switched, we have a different rule that we will eventually learn. But for the power rule, the base is a variable, the exponent is a constant. Then when I take the derivative, what happens is this exponent comes down in front to give the n, and then I subtract 1 to get my new exponent. The base doesn't change. And that's one of the things that people make mistakes on, is they want to change the base. We're not changing the base. So examples here. I have y equals x to the 4/3. It's a variable base, constant exponent, so I can do the power rule. So the 4/3 comes down in front. The base stays the same, and I subtract, I subtract 1 to get my new exponent. And there's my derivative. So this is going to tell me the slope of x to the 4/3 at any x value I want. So if x is 2, well, then the slope of my function would be 4/3 times 2 to the 1/3. Now, as weird as it seems, the power rule is also what allows me to take the derivative of radicals. And for this, we need to remember that I can rewrite radicals as exponents. And quite honestly, a lot of times in calculus, when we see radicals, we're going to rewrite them as exponents. So the index is the denominator of the exponent. So now I have a variable base, constant exponent. I can do the power rule. For the derivative, the 1/4 comes down in front. Base stays the same. Subtract 1 to get my new exponent. These last two examples are just ones because we see these a lot, and it's easy to make mistakes on these. So y equals x. To find the derivative of this, it is actually the power rule, because this is x to the first power. So I have a variable base, constant exponent. The 1 comes down in front. The base stays the same. I subtract 1 to get my new exponent. But then x to the 0 power is 1. So the derivative of x is 1. And that kind of makes sense because it's a linear function with a slope of 1. In the purple there, y equals the square root of x. We already talked about I can change the square root of x to be x to the 1/2 so that I can now do the power rule. So the 1/2 comes down in front, base stays the same, subtract 1 to get my new exponent. But you're going to see that this tends to get simplified. So this would be 1 over 2 times x to the 1/2, which is the same as 1 over 2 square root of x. With the derivative of the square root of x, you could actually see any of those forms. That's why I wanted to throw that one in here. So then our constant multiple rule. So my notation for the rule is a little bit different here because we now are dealing with function operations where I'm adding, subtracting, multiplying, and dividing functions. So I'm going to say u is a function. So every time we see a u, it's really a function. And then c is a constant. So this is the constant multiple rule because I have a constant c times a function u. And what this rule says is that when I have that, I can just pull the constant out and say it's c times the derivative of what's left. In other words, the derivative of the function. We tend to do this rule without really being conscious that we're doing this rule. It just kind of automatically happens. So here I've got g of x equals 5 times x to the third. That's a constant times a function, x to the third. So I can just hold on to the constant, and then the derivative of x to the third uses the power rule. So I have 3 times x squared for that derivative, which can be simplified to 15x squared. Typically, once you're comfortable with this rule, you'll skip this intermediate step and go straight to here. You'll just do the 3 times 5 when you pull the 3 down in front. Sum and difference rule, this is what combined with the constant multiple and power rule allows us to find derivatives of any polynomials. So u is a function and v is a function. So if I'm adding or subtracting functions and take the derivative, I can just do the derivative of each term and add and subtract all of those derivatives. So what it's really saying is when I look at this, instead of trying to do the derivative of the whole thing at once, I just start doing a derivative term by term. So the derivative of x squared requires the power rule, so it'd be 2 times x to the first. Then I have my plus sign. The derivative of 4x is the constant multiple rule, so the 4, times the derivative of x, which we saw in the power rule example is just 1, so that's going to be plus 4. Then I have my subtraction sign. The derivative of 3 is a constant, so the derivative of constant is always 0. Like with the constant multiple rule, we really don't think when we're doing this. We just go ahead and go straight to doing it, but we're doing it term by term. So far the rules have been pretty straightforward and have seemed actually a lot like our rules with limits. But now's where they start to get complicated. The product rule. So I'm dealing with two functions. U is a function and v is a function. And if I'm multiplying those, to find the derivative, it is not the derivative of the first times the derivative of second. That's not going to work out. What we do is we're going to take u times the derivative of v plus v times the derivative of u. I tend to think of this in words as it's the first times the derivative of second plus second times derivative of first. Other people like remember it in terms of the symbols, uv prime plus u prime v. But the key is I'm multiplying an original term times derivative of the other, and I'm doing it with both terms and then adding it. So here, the x squared plus 1 would be my u. The x cubed plus 3 would be the v. So I'd have first x squared plus 1 times the derivative of second, which would be 3x squared. Then I have plus the second, x cubed plus 3, times the derivative of the first, which would be 2x. And this would be a case where I'm really glad I don't have to simplify for the AP exam. I can leave my answer like this. That is my derivative. That will tell me the slope for any x I choose to plug in. With quotient rule, we're now dividing two functions. So I have u and v are both functions, but now I'm dividing them. This is the one that personally causes me the most challenge. So because it feels a little bit backwards. I've got a subtraction instead of addition like the product rule, and the order of what's being taken a derivative of is backwards from the product rule. So I always think of it in terms of words. I would take the bottom, v, times the derivative of the top, u prime, minus the top, u, times the derivative of the bottom, v prime, all over the bottom squared. So that's all over v squared. If you're someone who likes to have some music to help you remember things, like how you can sing quadratic formula to Pop Goes the Weasel, there's an entire musical called Calculus the Musical, and yes, I have seen it multiple times. The link here will take you to the Calculus the Musical website where you can listen to a song. It's about 20 seconds long, a song that will tell you the quotient rule. I have a couple students every year that's how they remember it. I will admit it's kind of a cheesy song, but it is effective. So here, my top, the x squared minus 1 is going to be u, and the x to the fourth plus 7 is my v. So when I want the derivative, because I'm dividing, it's the quotient rule. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And again, I'm not required to simplify, so I'm going to leave it just like that. One thing that I didn't mention with the product rule, but if you notice, me using parentheses, bottom squared, me using parentheses is really, really important in both the product rule and the quotient rule. You need the parentheses to make sure that the things that are multiplying are the correct things. Now, in terms of how the AP exam tests, do you know these properties? Some of it is they can just give you things like this and say find the derivative. But they also know that some people may prefer to use the definition of a derivative with the difference quotient. To see if you really know your rules for differentiation, they'll give you something like this, where they give you a table of information about two unknown functions. So here we're being told that u of 2 is 3, v of 2 is 1, u prime of 2 is -4, v prime of 2 is 2. And I'm being asked to find each derivative here. So to do this, I have to use the rules. So here I see the derivative of u times v. So that means the product rule. So that's first times derivative of second plus derivative of first times the second. And then from the table, I can plug in these values. So that's 3 times 2 plus, whoops, I messed this up. That should be a u prime here. This is a v prime. Sorry about that. U times v prime plus u prime times v. Okay, so u times v prime plus u prime times v. And I could leave this like this, but for people who feel compelled to simplify, that's going to be 2. For u divided by v, this is the quotient rule because I'm dividing. So I have bottom times derivative of top minus top times derivative of the bottom all over the bottom squared. Please notice I'm doing this with the symbols first and then worrying about the values. Make sure you're doing it in that order. Symbols first, then plug in values. Because if you plug in values first, you're always going to end up with derivative of constant, which is always 0. And they're not going to try to trick you like that. So find the derivative using symbols, then plug in the values from the table. So I have v, which is 1, times u prime minus, I did it again with writing these backwards. This is u prime, uv prime there. And I'm just having difficulties today with getting things in the right order. So that's 3 times 2 all over v squared. And again, I could leave it like that, or I can go ahead and actually simplify it and get negative 10. For the last one here, I can see because of the subtraction, I've got sum or difference, so I need the derivative of 2u, which is a constant multiple. So that's 2u prime, and my difference. And then for the derivative of 3v, that's also the constant multiple rule, so 3v prime. And then I can plug in from my table, u prime is negative 4, and v prime is 2. And again, I could leave it just like that because I'm not required to simplify. Or if you are compelled to simplify, that's negative 8 minus 6, which is negative 14.